Hey everybody, my name is Andy and going to do a stream on creating a NES emulator using Python 3. So yeah, welcome to the stream. This is going to be pretty based off the current emulator being created by Ferris, who's doing it in Rust and doing it for Nintendo 64, which I thought was super cool. So I thought I'd do the same thing, but do it a bit simpler. So do it for the NES, which is obviously a bit of an older system. Going to be a lot easier to do, allows to have a bit more fun with the language in particular, and it's going to be focusing on Python 3. So what are the features of Python 3 that I'm kind of looking to come into? So I am coming from a background of doing a lot of Python 2 development. I've never really messed around with Python 3, so I thought I'd come into it and do a bit of a series where we look at things like type hinting. So I might just pull up a Sublime window here. I've got the font sizes bumped up a bit, so this hopefully should be easy to read. So the idea will be to focus a bit on Python 3, like I said, and to get things like type hinting. So to give an example of what that's going to look like. So in Python 2, and in Python 3, you do not have static typing. What they have added in Python 3.5 is support for inline type hinting. So what this allows us to do is to say, instead of saying argument1 print arg1, instead we can say arg1 is of type integer or string or object or whatever we desire. So there's nothing in the Python interpreter that's actually going to read and ensure that this is correct, but it does mean that a linter can come through and take a look at it and make sure that all our object types are aligned. Other things like advanced unpacking seems pretty cool. Command line arguments are done a bit better in Python 3.2. There's keyword-only arguments and function calls. Generators and iterators have been redone, so everything is now an iterator if you're coming from a Python 2 background, or the standard library things, that is. And generators now have some new syntax, including yield from. There's built-in enums and things like mix-ins. Mix-ins were actually part of Python 2, but whatever. We're looking into many of them. Anyway. Cool. So what are we actually going to be doing in this? So the hope that I have is to write a NES emulator. So I have looked into this a bit before, and I have done some just kind of quick looking around at what was involved in the NES and kind of how to make an emulator. So to give some background, I have never made an emulator before, so this is going to be my first shot at it. We'll see how it goes. But I think I have done some CPU development before. Some CPU emulation before. So I've done some MIP assembly programming and created a CPU to emulate running those instructions. So I have a bit of familiarity with that, but I've never done any NES stuff before or any full emulation. So we'll see how we go. And what happens, basically the idea is I would just want to be doing all the Python coding on stream. I do have a repository set up for this, which is just a empty repository. It doesn't have any code or anything in it at the moment, just some readmes and stuff like that. And yeah, today just look into what the NES is, find some information about it, and start coding up a CPU emulator, potentially. Kind of the goal here is going to be to document the process of making an emulator, a pretty simple one, hopefully, and just learn some of the new features of Python 3. Obviously, if you've never used Python before, then could also be a good way to learn Python. Yeah, what do we want to do? We want to make it work. So ideally, that's going to be the end product, is something that works. There are plenty of other NES emulators out there. There are even NES emulators out there written in Python, so there's no great value to this, I would say, with the exception of learning. So, but look, we'll learn and see what we can make. Hopefully, have some fun and yeah, see where this takes us. The idea is not to have it be something that is going to be particularly fast. To be honest, I'm not really focusing on performance, just getting it worked, or feature filled, or anything like that. Yeah, one last thing would be obviously creating an emulator. You need to use ROMs, and the downloading and piracy and stuff like that of ROMs is kind of something that is definitely illegal and that Nintendo polices, so please don't post any illegal ROMs or links to places where you can find ROMs or stuff like that. And if you're going to be using an emulator, only use ROMs that you have ripped yourself. Cool. Alright, let's go take a look at the emulator and see what we can find out. Sorry, at the NES, and see what we can emulate, I should say. So, this is the Nintendo Entertainment System. So, kind of what it what it is a video game console that was released in the 80s. Yeah, in 1985. And basically, at its core, it's got a 8-bit CPU. So I have looked into some of this stuff, so I might just go through what I've kind of looked at. It's got an 8-bit CPU, which was made by these guys, by Rico, the 2A03, but really at its core, it's this MOS Technology 6502 CPU. So this is going to be what we're going to try emulating today. Now, I might just open up Sketchbook. Cool. And I might just do some of the basics, just a bit of a walkthrough of the basics of what an emulator does and how we can do it. Cool. So what is the NES? So I'm going to do some bad drawings over here, but so the NES is going to be, excuse the blocks. So if this is our NES, it's going to have several components. So the first one is going to be the original one that we're going to do. To create an emulator, you need to simulate each part of these components. So the first one is going to be a CPU. The second part over here is essentially the graphics card. It is called the PPU, which is the Picture Processing Unit. But this is the things that the CPU can push bits to, or push information to, and the PPU will render this on a screen, or render this in some way. So essentially the equivalent of a modern day graphics card. So all pretty standard. On the side here, we will have our memory. Now, this is going to be, well, I should call this our RAM, I suppose, which is just going to be able to store a lot of bytes. Now, everything that I'm going through here is kind of off the top of my head, so all of this is going to be rather approximate, but the answer is the CPU, which is this thing here, is going to be an 8-bit CPU for a NES. I'll kind of come back to this and explain what this means. But we're going to have an 8-bit CPU, and we have 2 kilobytes of RAM. Sorry, I might just adjust this a bit. Cool. Of RAM. There we go. And I don't actually know what the specs of the CPU are. I guess that's going to be something we're going to find out. And the idea is, with the NES, is that a lot of the data, most of the data actually, that the CPU gets from is going to come in off a cartridge which you put into the console, which is going to be read-only memory, which is why we call it a ROM. And so that's what the ROM part of a NES game is. So that's going to give us all the data about not only the code to play the game, but also any of the data that's on the game. So, you know, what's the configuration of in the case of Super Mario Bros., what's the configuration of a Mario sprite, this little person, but also what is the code that we need to run so that, you know, it'll have assembly instructions on here. Cool, so that's kind of what the emulator overall is going to look like. So what we are making is the NES. So what we're going to do is we're going to emulate a CPU. So we're going to have something that can read in instructions that are going to be loaded from the ROM. It's going to be able to interpret them. So it's going to read them in hex, turn them into things that the CPU can understand. It's going to be storing values in RAM and also in registers, which kind of just another bit of storage over here. And it's going to be telling the CPU what to do and what to draw. So we're also going to have to simulate the CPU and hook it up to some kind of graphics framework so we can actually see some output from that. We're going to have to simulate the RAM, so the memory and how that's all stored. Probably going to have to make things like a debugger and other things like that. Anyway, so that's kind of the core of what a CPU, of what the NES is. And what we're going to be doing at the start, at least for today, is going to be looking at the CPU and how we can simulate, making one of them. So it's how it can read instructions in and interpret that code and turn it into useful instructions. Alright, question. The cartridge didn't have its own RAM. That is a great question. I have no idea. Let's find out. So the reality is a ROM cartridge. The reality is a lot of these questions I'm not going to know the answer to, which is kind of why I'm going to be learning it all on the spot. So let's find out. A ROM. So I'm using Safari here with the text size bumped up a bit, but I might bump it up a bit more and see if that makes it any easier. Design. Alright, I don't know the answer to that, but kind of looking at this, my thought would be no. I believe there is some, on the NES, there is some persistent RAM. Oh, that's true, maybe on the, there is on the cartridge, because I think you can save things to the cartridge. You can have save files and stuff that are kind of in a long-term storage. But to be honest, here we go. So some cartridges have battery back static random access memory, allowing users to save game data, progress or scores between saves. That's a great point. So in this diagram down here, I suppose if I come back to this color, we will also have a small amount of RAM that the CPU can write to save things such as game state. Thank you. Como and S. Cool. Alright, so I might drill down onto what this CPU is and explain a bit further about what 8-bit means and all this kind of stuff. So if you've done any CPU work before, all of this is going to be fairly familiar to you. If you haven't, well then this might be a bit difficult to follow along, but I'll try and take it a bit slow and see what we can do. I might just, is there a way to increase this canvas size? Potentially. No, alright. Cool. Alright, new. I might as well save it. Cool. Alright, so what is the CPU? So this is kind of going to be a bit of a structure about what a CPU does. Hi, the code god. Hello, welcome. Thanks for coming along. So yeah, so the NES structure has this 6502 CPU. So the 6502 CPU, which I'll come look at here, is made by MOS Technology, Rockwell Cinetech. Anyway, so the point of it is, it's a old 8-bit microprocessor, and it runs its own version of assembly code. I'll kind of explain what these things mean. Kind of try to do it a bit step by step. So what is a CPU? So a CPU is, well, great question. I'm going to answer that in a fairly simplistic manner. A CPU is a piece of hardware that sits on the board, sits on a chipboard like the NES, for instance. It'll be one of the components on there. And the role of the CPU is to kind of be the brain of the computer. So it's going to interpret instructions from the operating system, potentially, or from the user. And it's going to communicate with things like our memory. It's going to read data from things like our ROMs, which in the NES's case is a cartridge. This is going to be our memory. And it also communicates with things like the picture processing unit. So the CPU is the thing that does all the interpreting and telling other things what to do. Yeah, also, if you do have any questions, feel free to chuck them out. I'm kind of coming at this with a bit of background knowledge, but to be honest, I'm going to be learning on the fly. So yeah, anything you want to chuck out, feel free to ask. So how do we talk to the CPU? Also, I should mention this now. I'll draw it over here. The CPU also maintains some internal memory called registers. Whoa. So in the case of the 6502, there are actually 3 registers. So 3 bytes of data that it can store, and they're called X, Y. These are terrible letters, but you get the point. X, Y, and A. So what these registers are ways for the CPU to, instead of having to store data in the RAM, which is quite slow to get data from the RAM, it can just store small amounts of data in these registers, which are located, I presume physically located on the CPU. I'm not actually sure how that works. But anyway, some kind of low latency memory that you can access and quickly do things with. And so most of the commands that are in the assembly language, which is the language used to speak to the CPU, are going to be dealing with pushing data or pulling data from these registers. Cool. What is memory? So memory, the RAM is just a way of storing lots of bytes. Registers are a way of storing a single byte, but really quickly. Cool. So how do we actually speak to this CPU? So CPUs, and this is where it's going to get a bit more technical. So CPUs understand. CPUs can read in instructions, but they actually can only read in binary. So they can only read in zeros and ones. So a typical instruction stream that might get sent to a CPU is going to look something like, zeros and ones all the way down, so on and so forth. And to a human, that's fairly uninterpretable, but to the CPU, it's going to know what this means based off an instruction set, which in this case is the 6502 instruction set, which basically just defines what configuration of 1 and 0 can the CPU read in and understand. And the way that a human can understand all of this is something called assembly. So what is assembly? So this right here, these ones and zeros we call binary. And what is assembly? So assembly is a fixed set of instructions that allow us, much in the same way that Python is a programming language, assembly defines a programming language that we can use. unlike Python, it is quite low level. So instead of things like calling a print function or, setting up a function declaration, typically things in assembly are going to be single instructions that have one very specific purpose. So for instance, an example instruction might be, I'm going to write this in pseudocode, but load a value, for instance, 7, into the register X, which is this register up here. So we want to be able to tell the CPU, hey, we want to load a value into a register or into memory or send it to the picture processing unit or something. So how do we do that? So assembly defines a spec of instructions that we can use that will allow us to send commands like this. So for instance, this command in 6502 assembly, which is the programming language we're going to be using, is going to look something like load X. So this is just the syntax that it would use. And you can load the number 7. So this is an example of a 6502 instruction that we might use, which is going to load the number 7 into the register X. There's other commands obviously that you can use. There's around 150 commands, I believe, that we're going to have to implement at some point, which are going to be fun, but there are some common characteristics, and this is a pretty simple CPU, so there's actually not that many. So how does the CPU, so this is what the program is going to write then. So this is a kind of a very low level language, but still understandable by humans. We can kind of read that and say we know what it's going to do. So how do we turn that into something that the computer is going to know how to read, which is zeros and ones? So basically there will be a compiler which is going to turn this command into binary, and it's going to do that by using the 6502 specification. So it will look at this, which is in assembly, and will say, how can I turn that into binary? And basically it will say, well, I know that the code for load X is 010100. I don't actually know the code, but let's pretend that it's that. And the value of number 7 in binary is 111. And then it'll pad some zeros here so it knows what it's talking about. So basically, if you look at this stream of binary, this is going to be the first thing saying, hey, we're going to load an instruction, and this is going to be the next thing saying, hey, we're going to load the number 7. Cool. So why do we have to pad stuff with this? So I'm just going to keep going deeper down this rabbit hole until we kind of get to what are we actually trying to implement here. So look, let me know if you don't understand anything or if you have any questions, but this is going to be the basic way I'm going to do it. And then once I've got through this, we'll start looking at the NES more specifically and start looking at actual code and so on and so forth. Cool. All right. Let's do another one. So with that in mind, what's the next step going to be? So we know that the NES has an 8-bit CPU. So again, what does an 8-bit CPU mean? So typically, when we're talking about computers, 8 bits can also be referred to as 1 byte. So there are 8 bits to a byte, and there's going to be in this, when I refer to 1 byte, I'm going to mean 8 bits. So what does 8 bits mean? So 8 bits actually means 8 binary digits. So for instance, 0000000 is a number represented in binary that is 8 bits wide, or has 8 bits, I suppose. And this corresponds to the number 0. I'm not going to go into binary, to be honest. There are obviously some good resources out there for learning binary, but I'll go the theory of what 8-bit means. So this is one potential value that you can store in 8 bits. Another potential value might be 0000010, which is going to represent the number 2. So you can see that there's going to be all these possibilities of numbers that we can store. And so we think, all right, what is the biggest number we can store? 1, 1, 1, 1, 1, 1, 1. What is this number? So the biggest number that you can represent with 8 bits or 8 binary things is going to be 255. That's meant to say 255, yeah. Is 255. So you can represent the number 0 all the way up to 255, which means there are, I might use a different color for this, there are 256 possible values that you can represent using 8 bits. Or another way of saying that is there are 256 potential values that you can represent using 1 byte. Cool, so what does that mean for us? So what we're saying here is that if this is an 8-bit CPU, what this means is basically we're going to be reading in, when we're reading in binary code, we're going to be reading in 8 bits at a time, or 8 zeros and ones at a time, which is also going to be called 1 byte. So we're reading in 1 byte at a time, and typically everything operates off a 1 byte system. So every register can only store 1 byte or 8 bits. Every location in memory, so in RAM, can only store 8 bits or 1 byte, so it can only store 256 values. So basically, a register can be from 0 to 200, any value from 0 to 255. A entry in the RAM can only be 0 to 255, so on. So, and if it's communicating, this is how it does it. So this is going to be an important concept, is this 8-bit 1 byte. There's another part to this, which is hexadecimal. So again, I'm probably not going to explain too much the concept of what hexadecimal is, but I'll go over it briefly. So hexadecimal is a base 16 system. And what that means is that a binary is going to be base 2. We've got decimal, which is the number system we typically use normally, is going to be base 10. And we've got hex is going to be 16, base 16. So what that means is that you can use 1 digit to represent any number up until 16. So if we were to count up from 0 in hexadecimal, it would be 0, 1, 2, 3, so on and so forth, 9. And instead of going to 10 here, like we would in decimal, which you'll notice a 10 is 2 digits. So instead of 10 transitioning to 2 digits, we have special characters. So A represents the number 10 in decimal, B represents the number 11, C 12, so on and so forth, D, E, F. And so F represents the number 15, and then to represent the number 16 in hexadecimal, you would just write 10. So 10 in hexadecimal represents the number 16 in decimal, which represents the number 10000, or maybe one less there, but you get the point. So there are different ways of writing numbers depending on the number system. They all mean the same thing, they're just different ways of writing it. Now, why is hexadecimal important? Hexadecimal is important because all the ROMs are going to come just as a collection of hex. And why do ROMs use hex? So if we're using a 8-bit system, one thing that we'll notice is that the largest number that we can store is 255, which you can see in decimal takes up 3 digits to write. In hexadecimal, to go from the range 0 to 255, excuse me, you can write the number 0 can be written as 0 in hex. Typically you write hex as 0x and then your hexadecimal number. And the biggest number that we can write is going to be 0xFF. So this is our biggest in 2 digits, is going to be F, and F corresponds to the number 255, which is the number we found here. Cool, so what does that mean? It just means that we can write anything in any number up to 255, takes 8 bits to write in binary, which is what we're going to use normally. And you can also represent that as any value from 0 to 255 can be represented in 2 hex characters. Cool, so what does that mean? It means that we want to use hex because it's going to be a lot easier for us to read instead of decimal. Instead of binary, because FF is a lot easier to read than 1111111. It's a lot less characters, and it makes a lot more sense than decimal because we're aligned to it, and there's a very clear mapping back to binary, and all our ROMs are going to use it. Cool. So what that means is that every time we look at a value in a register or a value in memory, typically it's going to store a value between 0 and 255. We're just going to write every value that we see as a hex character, so FF or something. So basically, what I'm trying to say is that you can represent any value as 8 bits, or 1 byte, or 2 hex characters. Can all be written the same way. Cool. So there's plenty of other stuff to go into about how the CPU works, and I'll go back to that, but there's more stuff to this, like how do you deal with overflow and stuff like that, but we'll come back to that later. That's all a bit too far. Alright. Nice. Let me just take a look at what I was going to say. Cool. Alright, I think at this point, it would be good to, let's start looking at the NES, let's start looking at the MOS, and then let's start running some Python code. So what I do have here is, I might just open up a ROM, which I have stored here. Now I'm using Sublime Text here, and there is a plugin in Sublime Text called Hex Viewer, which you can install, which is just this really cool way of looking at hex code and is going to be very helpful to us. Cool, so what is this? This is the Super Mario Brothers NES ROM. So it is a ROM, and this is what all our ROMs are going to look like. They are just a collection, so this is all our data in here. They're a collection of hex characters. And you can kind of see that we talked about earlier that hex characters, any 2 hex characters can represent 8 bits. So if you look at the highlighting here, it's highlighting 4E. So what it's saying is that that is the first 8 bits, or 1 byte. And then 45 is going to be the next 1 byte. So if we were a CPU, we would actually be reading in 4E as one step. The next thing we would be reading in 4.5, then 5.3. So one cool thing about this hex inspector is that it shows us what is the binary. So it shows us that 4E actually represents the value 01001110. And it also tells us what the decimal value of that is, which is 78. So we have a 78 value here in this first byte. And what does this actually represent? So we're not in the code section of the ROM yet. We're just in the data section. And what does this represent? So we can see over here that the word 78, if you look up an ASCII chart, again, I'm not going to explain what ASCII is, but it's just, well, not in too much depth. It's a way of mapping numbers to characters. So we know that the number 78 corresponds to the letter N. The number the hex number 45 corresponds to 69, which corresponds to the letter E, so on and so forth. And so we can see that it's written out NES here, for the Nintendo Entertainment System, which is cool, because this is what we want. So we can see that this is a NES ROM, and then we can see that the rest of the data is either going to be program code, so it doesn't really have any meaning anymore in terms of ASCII. These are going to be instructions that we're going to be reading in and trying to determine what they are and what they're trying to tell us. So this is what we're actually going to read in and turn into something that works and can play Super Mario Brothers, ideally. Cool, alright. I'll go back to the Nintendo Entertainment System. So we're going to start by doing the CPU, and we might start going into some code now, into some Python code, and just, yeah, try and smash some stuff out. So the idea is that the MOS6502, which is this thing, uses an assembly language set for its own thing called the 6502 instruction set, or something like that. And basically, there's a table here on Wikipedia which lists all the possible instructions that you can write in this assembly language, which will then be converted into valid code. I'm not going to go through all these things, and there's different ways of things that do different things, and they have different ways of addressing which memory to look at or which registers and stuff like that. But for now, screw that. Let's just go do some Python and try and read in the ROM and start printing things out one byte at a time. Cool, so as I said, I've got a repo set up here called the Python NES. There's no code in it, and I do use the PyCharm editor, which I quite like. Obviously, it's not required. You can be able to, all this code will be uploaded, and you'll be able to look at it in anything, but for now, I'm going to be using that to do everything. So what are we going to do? We'll create a new Python file. We're just going to call it main for now, because we're very uncreative. Do I want to add this to Git? Yes. Cool. So for starters, we've got to ensure that this is in Python 3, which at the moment, I do believe it is. Yes, it is. But I might just set up a virtual environment so that we can run the code in that, and I'll just kind of show you how to do that. I'm not going to go into installing virtual environment and stuff like that. There are plenty of tutorials around, but the process, if you have virtual environment wrapper, is just going to be make virtual env NES. That's just going to install a Python 3.5.1 virtual environment, which is what we're going to use. Cool. And we now, if I deactivate this, I can use the work on command. So work on NES will activate that virtual environment, and deactivate will deactivate it. So we now have a virtual environment where we can control the packages that are going to be installed and how things like that work. PyCharm, I'll just come into here, I'll go down to the project, and I'll just change the project interpreter to use the correct one. So I will add the virtual environment that we just created, which is going to be somewhere up here. In users andrew.virtualenvironments. Oh, no. Yeah, there it is. So this is our virtual environment, and then we can just come down here, we'll go to bin, Python. Cool, alright, so we're now using the correct virtual environment. Alright, I want to run this file, so I'll just do the standard if name equals main, run the main function, def main, and we're just going to print hello world. So this is going to be our first Python 3 thing, if you're coming from Python 2 background, is that print is now a function, which is pretty cool, and it has some special syntax and stuff like that, but this will work. So calling print without the function brackets now, so calling it as an operator, will no longer work, and it'll give you a syntax error. Cool, alright, let's run main. Alright, so we have run using our virtual environment, we have run this Python file, we can see hello world. So we now have a working Python program. It prints hello world, but that's all we want to do for now. Cool, so what do we want to do now? We want to read in the ROM. So the two things that we're going to do here is, one, we're going to do some command line arguments. So we want to be able to pass in the location of the ROM so that we're not hard coding it, so that anyone can run this and pass in their own ROM. And we also want to be able to open that file and start reading it in. So that's going to be doing some file stuff and some read lines. We want some command line arguments, And yeah, cool. Well, let's do that pretty quickly. So how do we do command line arguments in Python 3? So that has changed in Python 3.2. Again, I've only recently transitioned to Python 3, so my knowledge of this kind of stuff is fairly lacking. So, yeah, we're just going to go look it up. I know that it exists, but I don't really know command line arguments. Argparse, no? Yeah, the Python 3 includes argparse. So I think this has all been backported to Python 2.7, but running it natively in Python 3 seems cool. Alright, and this will allow us to do on the command line to show help and to do stuff like this. Right, so here's our code. I'm gonna be bad and I'm gonna copy and paste this and then just change it. Ideally we should be understanding things, but for now. So I'm gonna need to import the argparse package. It's an argument package description NES emulator, and we're going to add one argument, which is just going to be the path to ROM, path to NES ROM. So now these kind of fields here, we're going to need to go and figure out what these mean, because I don't know what they mean. Cool. Alright. A meta variable is going to tell us how it's going to be formatted in the add argument. Here we go. Cool, so this is kind of how it's going to go from here on in. I will just try to write some Python code to learn some things and try and focus on some of the Python 3 stuff. We should move pretty quickly and yeah, see where we go. Yeah, also if you have any comments or ideas, if text size is too small or something, let me know and I'll try and bump it up or something. Alright, God, this is some documentation. Type, cool. Int open. Which can take file type. Cool, so we can actually pass in a file. That seems cool. I'm not going to do that though. I'm just going to do things manually. We don't need more arguments. Meta variable, whatever. We'll just call it ROM. And the type is going to be string. Parse args. Strings? Is this how this works? Cool. So let's run that, see what we do. The following arguments are required. That is correct. We have added a ROM path thing. So we need to add this as a command line argument, so we can add this in here. And it's going to be in my ROM. It's going to be in /users/andrew/ROMs. I'll just have to verify that that is correct. And it's called smb.nes. So all we're doing here is passing in a path that can be used on the command line. Cool. Sweet. So you can see that we have an args object here, which has an object which is a string called ROMPath. I'm not sure what this accumulate function does, to be honest, having not used this before. Args.accumulate, that was their thing. Okay, so this is kind of useless. So what we want is args.ROMPath. So instead of printing hello world, we're going to print the ROMPath. Cool. So we now have the path to our ROM. So what do we want to do now is, so let's just get some documentation going on here and then we can go forward from there. Yeah, pass the args. We'll come back and make sure that this ROM path is correct later. For now, I'm not gonna bother doing it. All right, so I presume that file open in Python 3 is kind of similar to Python 2. We'll presume that we have some valid input for now. That may or may not be true. So we want to open, so this is kind of non-Python 3 syntax, but for those who haven't seen it before, you could do something like file equals this. So this will open the file, and then you can read out the data or whatever, and then when you're done with it, you close it, because otherwise you will have an open file which sticks around for the execution of your program, which isn't great. So the good way of doing this typically is going to be using this with syntax. So if we say with this as file, so now this will assign the opened file to a local variable called file, and then down in this indent here we will be able to use it, so file.read. And when this block goes out of scope, so for instance when we come back to this code, when we come back to this line here, this file will be automatically closed because it will be taken out of scope. So it's just a nice way of managing I/O, is wrapping something like this so you don't have to remember to close your files. Cool, so let's read lines. Cool, so Python, if you open a file, you can read the lines. Now, if I do print file.readlines, I presume that's going to work. Potentially, this is going to read them out in the wrong format because we're not opening this in the correct mode. I think we might need to open it in binary mode or whatever it is, but we will find out. So UTF-8 codec can't decode byte, yada yada, invalid start byte. Cool, so what does this mean? It means that we have opened this in the wrong format, which is kind of what I expected. So Python open file, let's find the Python documentation on this. Python 2.7, so I presumed it has not changed. Ooh, no, is not what I'm looking for. So now, this is terrible. Python open. Alright, maybe it isn't here. Yeah, mode. So B is for opening it in binary mode. So RB is going to be what we want, I presume. Cool, perfect. So we're in Python 3 and we're loading in a file. Now it's all these weird characters, and you can see what it is here is that it's a binary string, and so it's actually loading in and printing it out as its ASCII equivalent. And so obviously a lot of these don't have defined ASCII equivalents because they're just random collection of hex files, but you know, that's fine for now. So what we actually want to be doing is, instead of this, is reading it in as hex. So I wonder if there's a way to do that. One way to go find out. Read multiple bytes in a hexadecimal file. That sounds like us. Cool, so it looks like we do have the right thing. And if we store this in a variable, maybe we can look and we can see. So one disadvantage of this, putting it in this file, in this with construct, is anything that we declare in here, if we try and access it out, oh, you can, maybe. No, I don't. No. Oh, cool. Didn't know that. I thought that would have been. Alright, you can access it. Never mind me. Just the file that goes out of scope. Alright, so print lines. So let's set a debug point here. And let's run it. Let's see what lines looks like. So this might be a bit small, unfortunately. But anyway, we can see that this file is separated into 300 lines. And each line is just a collection of bytes. So if we want to read out the first one, we can go line 0. So this is kind of one of the reasons I use PyCharm, is that the debugger is quite nice. You can drill down into stuff. You can put watches on things, and you can just really get a sense of what's going on. So this is the bytes that are on the first line. Cool. All right. What if we say, what is the 0th byte? So we can see that the first byte is going to be 78. So if we come back to our hex viewer and we look at this, we can see that indeed our first byte is meant to be 78, and the next byte, this is obviously in decimal, but that's fine. We can, if we have it in decimal, we can convert it to binary or to whatever. Is going to be 45. Should be 45. So if I do lines 0, 1, it should be 69. Sorry. Yeah, the decimal version. Cool. All right. Let's keep going then. Just as a side point, I can play some music while I'm doing this. Don't know if that's something that people want, but at this stage I'm not going to do it. But if you'd like me to put some music on kind of while I'm speaking, then yeah, let me know in chat. Cool. What's going to be next? We've got our file ready now. So kind of what we're going to want to be doing now is to be setting up a very basic CPU structure and probably passing through the first instruction to it. So obviously we're not going to get many instructions done, but it would be pretty cool today to try and get one instruction implemented and to be able to read that in. As I said, the bytes that we're reading in at the moment are actually just data. But at some point this will turn into program code. We can figure out where that is. That's going to depend on the NES and where it starts its code and where the data begins. But for now, we're just going to start creating a CPU and pretend that we're going to pass in an instruction to it. So potentially, instead of reading this in through the file, we might just do this through a test harness, just to make it a bit easier for us to check that what we're doing is correct. Cool. All right. Let's create a CPU file. So CPU. So another thing that's in Python 3 is that all objects should inherit from this base object. This is actually in Python 2 as well, but it's optional in Python 2. This is you can do it in Python 3 as well. There you go. Anyway, the convention I believe in Python 3 is to use this object thing, and it gives us access to these new style classes, which we use in Python 3, which are pretty nice. Anyway, let's chuck in an init function. For the moment, we're probably just going to define some basic things. So what does the CPU need to do? So CPU is a collection of, what does it need to store? It has registers that it needs to store. So for the moment, we can just say self.registers, and we'll just store them. We'll just say that's an array for now. Come back and put a proper implementation in later. What else does the CPU need to do? Need to store. Can't think of anything else off the top of my head, although I'm sure there's many things. It'll probably need to store references to the other things that it can talk to, but potentially might talk to them through some kind of interface, probably a bus class that we will create, so I won't do that. So what does a CPU need to do? It needs to be able to interpret and execute an instruction. As a point, I don't actually know whether there's any pipelining in this CPU. It's something to probably look into, but that's a bit far down the line. That's further down the line. Cool, so let's call it a process instruction function. Now, we were talking before about things in Python 3, and one of them is type hinting. So this is kind of what I want to be doing, is to mess around with this type hinting stuff, which is kind of new inline in Python 3.5, which I haven't played around with yet, so you'll have to stick with me here while I try and figure it out. But process instruction is going to take in a instruction. For the moment, we're going to say that is I don't actually know what that's going to be. It's probably going to be its own class, but we'll make it a string. And it's not going to return anything. I believe it doesn't need to return anything. We can just leave off the type hinting. Cool, so this is the syntax again for how you can pass in type hints. So this is saying we're going to have an instruction variable parameter, which is going to be passed in, and it's going to have a type of string. And now if we try to call this without passing in a string to it, the linter is going to complain at us. Cool, alright. And we'll just say here, to do is process the instruction. Pep8 is always good. Alright. So we are loading the ROM. Let's create our CPU. We import CPU.cpu. There's no arguments. Now, if we call cpu.processInstructions, instruction is unfilled, and if we try and pass that an integer, it's going to throw us an error because it's telling us that we expected a type string and we got an int instead. Perfect. So what that's saying is that our type hinting is working. So let's pass it lines 0, and let's pass it the first 3 bytes. Now, what expected string got union int? Oh, that's not how you do string splicing in Python then. I have no idea how to do that. Lines 0, I believe, is bytes. How do you splice bytes? God. Alright. Built-in types, bytes. So it's a sequence type, that makes sense. Bytes are sequences of integers between 0 and 255, so this makes sense. We were talking before about this being an 8-bit CPU, and therefore it having being 1 byte, which is between 0 and 255, so we're representing things in bytes. Nice. Alright, this means for the byte or byte array, B0 will be an integer, while B01 will be a byte array object of length 1. Alright. You can convert a bytes object into a list of integers using list B. I don't know if we actually want to do that. So what that's telling us is that this is an integer line 0 should be a collection of bytes. Line 0, 0 to 2, yeah, is also a collection of bytes. Cool. Now, we're not actually passing in a string, obviously. What do we got? Union int bytes instead. So what it's telling us, so this is the type hinting. It has some new built-ins. So for instance, if you want to pass in a list, you can type list and you can import it from this new module called typing, which is new on 3.5. So it looks like, if I say bytes, is this going to work? Cool. Yeah, we are passing in a collection of bytes. But if I was passing in a list of integers, so if I cast that to list, I could call list int, I think is the syntax. But it's not, it's some bytes. Alright, so an instruction is going to be made up of multiple bytes. Again, we might replace this later by a class, but whatever. And we're just going to print those bytes. Oops, print the instruction, I mean. Process instruction, maybe static. Yeah, fair enough. Cool, alright. Let's give that a run. And that should print BNE. So we actually want to print the first 3. NES. Alright, so we now have 3 bytes that we are loading in, which are the first 3 bytes. So typically instructions in the, let's go back and look at the MOSFET 6502. So typically instructions are going to be 2 or 3 bytes long. So you'll have 1 byte that will be an identifier for what the instruction is. So you can see here, high, low, so that something that is 8.4, the hex character 8.4 is going to be the store in Y operation. And then depending on whether there's one thing here or a comma here, so this will have a single data option, so it'll be 2 bytes in total, whereas this will have 2 data options and therefore will be 3 bytes in total. So yeah, so let's presume for now that we're only going to be dealing with, well, our first one will be a 2 byte instruction. There is a very good page on 6502, well, how do I say this better? There is a fantastic wiki on NESDev called nesdev.com. They've got a wiki, wiki.nesdev.com. NES reference guide, which will basically tell you everything you need to know about the NES. From file formats to the CPU to anything else. So I'm probably going to be using this extensively. But at the moment, since we're just starting off, I haven't really referred to it. There is also a great website called skildrick.github.io. So it's a GitHub pages page in which he has some really cool JavaScript things that he've written that can actually compile 6502 assembly code. So this is an example of some assembly code. So load into the A register the value 1, store that value in memory location 0200, load into A the value 5, store it in 201. In this thing here, he actually represents the memory locations. If you store a value in them, it comes out as a color. So if we run this, we can see that we're loading 1 into this pixel, 5 into this pixel, which represent different colors. Cool. So he does that using JavaScript, and you can monitor. You can see the memory here. So if you look down to 0200, wherever that is. Ooh. Yeah, you need to do more memory, but whatever. So he is drawing this to the screen. So it's got some really good examples of how the 6502 assembler works and what you can do with it. Sweet. All right. So let's take his example program, which is going to be load A, put it into 1, and let's think about how we could potentially interpret interpret this. So for now, instead of reading in the ROM, well, we're reading in the ROM, but instead of actually processing the ROM instructions, I just want to do a single, be able to do a single 6502 instruction. So if we click the hex dump button here, actually even better, the disassemble button, it'll tell us that the LDA01, this gets turned into hex 0901. And what that actually then gets turned into is a collection of binary characters. So if I say A9, A901, I might dump this into a new file, and I will save this in my ROMs as test.hex. Cool. 69. Perfect. So now when I come back to here, I'll create a new configuration, which is going to be called the test ROM. And in my command line argument, instead of calling that, I'll pass in test.hex. So now when we run this, well, that should be passing in our text ROM, and the first bytes that we're going to get are going to be A9, which is, oh, interesting. Which is physically the bytes A9. That's a bit confusing. Oh, let's take a look at what lines is. Right, so it's not reading it in. Yeah, it's not actually saved in hex. It's just pretending to be saved in hex. I suppose that then becomes a great question of how do we save something in hex? I don't know. Well, let's do it a cheat way. Let's copy this Super Mario Brothers NES. Let's call it test.nes. Let's open it up here. Okay. Never mind that. That's a bad idea. Let's figure out where the NES starts programming. And let's actually take some real instructions then. Alright. CPU. File format. NES. So the CPU, so the CPU's got to run at a fixed frequency as well. So we're going to have to do that. And it's going to have to be reading in one instruction at a time. And the reality of the CPU is that each cycle has to do a read or a write. Yeah, the APU is also contained in the same chip, which is the audio processing unit. So we're going to do audio. Yeah, so there are, because it's an 8-bit processor, similar to everything else, there are going to be 256 possible instructions that we can run. The reality is going to be that not all of them are real instructions. I think only around 150 of them are. Oh well, see what we can do. Right. NES is the de facto standard. An INES consists of the following sections: a header, correct, we can see that has the first 16 characters to round 0. Yeah, so these ones are the header. So what it's telling us is you've got the letters NES, and then some, I don't know, probably some check digits or something, and then just blank data. A trainer, no idea. PRG ROM data, sounds promising. CHR ROM data, I don't know what these acronyms mean, but I guess we can find out. So as I said, while I've done CPU stuff before, and I've done some assembly stuff before, I've worked with MIPS before a bit, but I've never done emulator stuff or NES stuff. So a lot of these things are going to be new to me, as new as they are to you, I presume. All right, the format of the header. Yeah, okay. So NES followed by an end of file. The size of the PRG ROM. Cool. So NES, and then this is our check digit. So 02 is going to tell us the size of the PRG ROM in 16 kilobyte units. So we have a 32 kilobyte PRG ROM, and then the next value is 01. So we're going to have a 8 kilobyte CHR ROM. Flags. So what are these flags? Okay. So whether it has RAM or horizontal mirroring or whatever, we probably don't need to worry about that for now. Size of the PRG RAM. Byte 8. 0. So we want the number 7. Yeah, so this is the size of the RAM is 0. Value 0 infers 8 kilobyte for compatibility. Okay, so we have 32 PRG ROM, 8 kilobyte PRG RAM, and 8 kilobyte CHR ROM. Bytes, whatever, don't really care about them. So what is PRG versus CHR? PRG, presumably program, but PRG RAM circuit. Yeah, this one applies blah blah blah, even for discrete boards. I have no idea. Yeah, here we go. That's easy. So the NES cartridge has at least 2 memory chips on it. PRG, connected to the CPU, and CHR. Right, so CHR is going to be where we store our sprite data, presumably. And PRG is going to be where we store our program. I wonder what CHR stands for. Alright, there is always at least one PRG ROM, and there may be an additional PRG RAM. So PRG is going to be something that's connected to the CPU. So we're going to read data from the PRG ROM, presumably our program code, and we're going to write data, such as save file, to the PRG RAM. Some cartridges have CHR ROM, which hold a set of graphics tile data. Cool. Alright, cool. So presumably our PRG ROM, is going to start, we have 32 kilobytes of it, times x bytes, where x is 2 in this case, so we're going to have 32 kilobytes starting Trainer if present. I wonder if the trainer is present. Cool, so a trainer at this stored before the data is if flags 6. Right. So we're going to need to convert flag 6 to binary. And see what is flag 0, 1, 2. Is this flag 6? There's the header. That's the PRG ROM, PRG CHR ROM. Flag 6 is this, is 0, 1. Cool, so 0, 1 in binary means that every bit except bit number 1 is going to be off. So this flag 6 thing, no. Oh, that's going to be 2 in binary. It's going to be this bit is going to be off. The 0th bit is going to be on. So we're saying that vertical arrangement, horizontal mirroring. Cool. Probably don't care about that. We can flip that later. But what we're saying is 5 to bit 12 trainer is only on if the second bit of that flag 6 is on. That's going to be false. So the PRG data should hypothetically start after the header, after 16 bytes. And it should run for 32 kilobytes. Okay, so it should start at 0. If we look down here for the address, it should start at 0, 1, 0. So this should be our program code from here on. Alright, I can deal with that. Let's copy out some bytes here. Let's go to back to our page here, and let's try and figure out what these codes actually mean. So what was it? 78 D8 A9. So what is a 7-8 instruction? So row 7, so this one. Number 8 SEI. I suppose that's feasible. So these instructions are going to have no data bits. So actually this 7-8 is going to be a single instruction. And then this D8 A9 is going to be another instruction, presumably. So what's D8? D. Which one's D? D8. Alright, and that one. What's A9? Alright. Does this seem feasible? A9. Load A. Alright, that looks quite promising. So we've got two things that, I don't know what SEI and whatever the other one do, but something, and then we're going to load a value into register A. So this looks like it may well be our program code. And then presumably the next couple of bits will tell us, 10 AD will tell us which bits we want to load into A. Cool. Cool. So let's go to PyCharm. So we are going to say that let's just pass in the first line. Actually, how long is lines? Lines 0. Oh, right. Let's go back to main. Line 0. Let's get the length of lines 0. 45. Alright, so if we strip away the first, we'll say instructions equals lines 0. We'll just look at the first line for now, and we know that there's a 16-bit header, so we'll just say take it from 16 on. Let's look at instructions. This might be complicated. 3. 5. Oh yeah, that should be right. So 15 should be 0, and then 16 should be some. Yep, so if we take it from 16, and we go all the way to the end. Yeah, I'm not sure if that's correctly indexing our bytes. That's a great question, isn't it? What if I do file.read? See what lines comes up as. So lines is bytes. Right, so this is going to read the entire thing, isn't it? So I probably want that instead of read lines. But we still want this, but without that. Cool. So now the 0th byte is 120. Okay, so instructions start from 16 and go on until 32 kilobytes. They last for 32 kilobytes, which is from 16 to 16 plus 32. Oh, what are kilobyte calculations? 32168 or roughly, something like that. 16384 times that many bytes. So we'll want to come back and not hard code this. Unhard code. Number of PRG blocks is going to be 2 in this ROM, but we'll just make it. We'll make it do that for now. So now we're going to load in all our instructions. So this instructions thing should be 32768, which sounds around right to me. Should be this times 2. Correct. So we have 32 kilobytes. Each one of those entries represents a single byte of data. We can probably put all these constants and pull them into their own configuration thing that can read the header, so header reader or something. There's also going to be a fair amount of stuff that needs to be done with there's going to be a fair amount of stuff that needs to be done with configuration and boot up status and stuff like that to set the initial state of the CPU. Again, we can come back and do that later. Alright, cool. So we've got our instructions. We can now read them in one at a time. So let's do a for loop. So for an instruction in instructions, we're going to pass in that instruction. Instructions. Is that a problem? Is instructions not iterable? Okay. If I turn that into a list of instructions, will that not complain? Yeah. Ideally, you probably wouldn't want to turn it into a list. actually. I don't know about that. I'll leave that as that for now. Doesn't really matter because I believe that instruction is going to come out as an int anyway. Alright. Process instruction. Print instruction. Let's just break after one loop of this and check that we are indeed. Yeah, so we're getting our first byte, which is 120. Now, bytes. Yeah, expected and iterable. Bytes are weird. I don't know. Cool. We're actually passing in an int, technically, but let's just create a class where we can store instructions. So another thing I'm going to be trying to use here is mixins. So instructions are going to be a collection of two things. One, they're going to have a purpose, so they're going to load into a register or they're going to do something else. And two, they're going to have an addressing mode. So one of the features of 6502 is that it has a lot of different modes to address things in. So you can say, grab me this, you know, to put in register A, I want to put the number 7. Or alternatively, I want to put in whatever's in memory location, this memory location, or alternatively, I want to put in whatever's in memory location that is 200 ahead of me or 200 behind me, or that is a memory location that's stored in another memory location, and you know, stuff like that. So there's all these different ways, which are going to be consistent, I think, between all the instructions. So basically, we're going to have some kind of mix-ins that allow it to be addressable, or in some instructions are not addressable, but also addressable in different ways and stuff like that. For now, we'll just have a class though. Instruction. It should probably be called instruction as well. Cool. And we'll make it a new style object. We'll chuck in an init. So what is this going to store? So this is actually going to take in a byte. And I mean, it actually gets passed in as an int. I kind of want to store it as... I need to figure out how we can cast things to binary. It's going to be important to figure out. As well as casting them to hex. But for the moment, I'll pass it as an int. So it's actually going to have a code that it starts off with, which is going to be a single byte, which is going to be an int. I'm going to call this an identifier byte. So this is going to be what this table... Let's get rid of some of this. This is going to be what this table is telling you. So the identifier byte is going to be, it's going to tell you that, you know, if it's 65, it's going to tell you that it's an ADC operation. So that's why we need that. There's actually going to be a dynamic amount of data that it needs to pull in based on the length. It's going to be interesting. So basically, unlike a MIPS or a similar instruction language, there's actually not a fixed instruction length. So for instance, in MIPS, all instructions, or you know, in the one that I was using, all instructions are going to be 32 bits long. So a program might look like this, right? Whatever. They might be different, but they'll all be the same length. In 6502, what we're going to have is that depending on the type of indexing that you're using, there's going to be a different amount of data that you need to pull for each instruction. So some instructions might take up 3 bytes. So it might be, you know, FF. Other ones might be take up 2 bytes, and other ones are just going to take up 1 byte. So this identifier byte is going to be the first byte in all of these, but then we're going to need to pull more or less data depending on what the type of instruction is. And I think that's going to come back to how our mix-ins are going to work. This is why I kind of want to do it through mix-ins instead of through inheritance, was because it would be cool to have different classes just be able to pick which type of indexing they want, but not have it be a distinguishing feature. So not have it be an inherited, well, directly inherited. And then that mixin can figure out how much data it needs to pull and how to do that. But for now, we'll just say it's got an identifier byte and we'll store it. Sweet. All right. So we've now got, well, let's do that. So we're really taking a byte, and then we're going to say instruction equals. Import that. We're showing us ourselves that it's an int, which it is, which is good. Look, I'm going to turn this into a list for now so it stops complaining. I'll try and figure out later how to do that properly. List might be bad because, well, I mean, I suppose it's already in a list, but there's no point casting something to a list, given it's already an iterable. Well, it doesn't think it's iterable, but it is. I'll figure out how to do that later. Cool, so we want to, so I'm just going to pull this out. So instruction is now over here, just split the window. Cool, so what does the instruction tell us to do? We want it to have a property, a method that's going to process. Now, presumably, we're going to make instruction a base class, and we're going to have different instructions implement different versions of this class, which implement different process methods. So, for instance, for a load A instruction, it would come down and, self.cpu, presume we have a link to the CPU somehow, dot A, registers.A is, equal to 7, right? So that's what the LDA thing might do, whereas a different one will do something completely different. What's there? Yeah, that is a great question, KDX. So I should write that out more explicitly. So what I've kind of been looking at is this NES file format. So what it is basically a header of 16 bytes, and then your trainer, which is not present in this case, and then all your program data. So what that is trying to figure out where our program data begins. So we have a 16-byte header, and then we know that our program data is going to be 16. This is 16 kilobytes times x, and this x is going to be given to us in the header. So I'm going to write this out with some constants because you're right, that doesn't actually make any sense. So the header size, really these should be constants. So there's going to be a header that is the start of every ROM, and then there is going to be, so basically we want to look at all the lines in the ROM, all the bytes in the ROM, sorry. Again, this should probably just say bytes. Bytes is a reserve word though. ROM bytes. Cool, so we want to take a look at the ROM bytes, and then we want to start at the header, and we want to go from the header until we hit 16 kilobytes times the number of programming bobs. So KB16. It's a terrible variable name, but you get the point. So basically, no, that's not Pepe. Hey. I might put some brackets in here as well to make this more clear. So what we're doing is we start at the header size, which if we look at the ROM is going to be these bits. So these are not part of our code, and everything from here on is the next 32 kilobytes. So we're going to start at 16, and then we're going to go from 16 to 16 kilobytes times how many programming blocks there are. And the number of programming blocks is actually whatever this value is set to. So there's two 16 kilobyte blocks, and that's defined in the header specification. Hopefully that clears it up a bit. Presumably I'll come back and change this. KB. That's a great point. I will do that. 16 times KB. So program data and lasts for a set number of 16 kilobyte blocks. Cool. Variable in function. Yeah, okay. So we have 16 kilobyte blocks. We will pull this number out later. Unhard code, pull from ROM header. Thank you. What? KDEX. Thanks for that. That's good. All right. So let's go through and let's just say that this doesn't do anything, and we're going to make this a instruction should be a the term I'm looking for is abstract class. So now I don't actually know if Python 3 does abstract classes any differently. Let's find out. Command line. Yep, okay. ABC doesn't look like it has changed. So this is kind of one of the weird things about Python is that to do abstract classes, you've got to inherit, or not inherit, you've got to implement this ABC thing, which I can never remember how to do. In Python 3.4 and above, you can inherit from ABC. Ah, there you go. So that was the old weird thing in the old Python. You need to specify your meta class as ABC meta, which was a bit weird. So this is how you do it in Python 2. In Python 3.4, we can just inherit from ABC, which is super cool. Love your code. It's pretty clear. Thank you. Comoandus? Let me know if that's right. Yeah, I'm using the Darkly theme on PyCharm, which is super pretty. And yeah, we'll try and make it as nice as possible. So this is actually, instead of inheriting from object, this is going to inherit from ABC. We're going to import abc.abc. This code might get a bit messier as we go on, but it should stay pretty nice because I think the NES emulator is not going to be too crazy. That being said, I've never done an emulator before fully, so we'll find out. So abstract method. So I'm going to presume that people know how inheritance works and how abstract classes work, but the way that you do it in Python is with these decorators. So function decorators use these at symbol, and they're going to stick around above any function you want to annotate and basically tell you something about it. So we're telling whoever inherits from instruction that it's actually got to have, it's got to implement this process function. And you can just call parsing here because you know that, well, we could do something in here, and then if the base class calls super, this code will get run. But, you know, for now, we're just going to not do that. Actually, we should. I'm going to make it print. So a cool way is, yeah, someone looking over my shoulder. Alright, a cool way of doing this is in Python 2 as well, I presume, but the format code in Python 3 is basically, it allows you to pass in a string, and I believe that's the syntax, is pass in, you know, our identifier byte. God. So we want to pass in an identifier byte, and we want to fill up this value and format it with the value that's in our variable. So now if we call super.process, it will print out the thing. Now I'll separate this later, but let's begin with a load A, because that was a command that we saw. Instruction, which is going to inherit from instruction. Now, init, I might need to override and do different things with, depending on the instruction, but for now, I'm just going to override process. So another cool thing, Python 3, is that super now doesn't need to be passed in in Python 2 you use, forget the exact syntax, but something like you had to pass in the class name and then call. Anyway, super just works now, so you can call super.process. And that will call the parents function, which is a lot cleaner. So we're not going to do anything else for now in that, and we'll pretend for now that this is going to be an LDA. Everything is going to be an LDA instruction. Cool. This is cool. So now when we process an instruction, we're actually going to receive an instruction here. Now we're going to have to import that. And when we pass instruction in, so that type error now went away because thanks to linting, we're actually going to, I actually just thought about something to do back here, but we're actually going to, instead of saying print instruction, we're going to call instruction.process. Cool. Now, the CPU can also do other stuff here. Potentially, this is where we're going to figure out which data needs to be passed into the function. And then we can, work from there. All right. Let's see if that works. It can be static. Yeah, fair enough. We'll make it non-static later. Another cool thing about PyCharm is you can really easily reformat and make sure things are pep8, but you can also optimize your import. So anything you're not using anymore just gets chucked out, which is super handy when you're, forget that you're using different classes and just make your code cleaner, which is what we want, right? Cool. So this is not actually how we're going to iterate through this list, but let's just check that this works for now. Cool. So we are taking the first instruction, we're passing it to the CPU, we are pretending it's an LDA instruction, and we're calling the process method, which calls super.process, which is saying the identifier byte is 120. Sweet. All right. So what do we actually want to do now? If we think about this, the CPU is probably the one that should be running this code. And instead of iterating through the bytes, really it wants to be reading one instruction at a time. So the way it's probably going to be doing that is by simulating what's called the program counter. So if I go back to here. So if we imagine that every line of code, LDA, store the number 7 and then store the number 8 for some reason. If you want to override it, store the number 9. Now, if these are all stored, this is stored at memory location 0, this is stored at 1, this is stored at 2. Basically what we'll have is we'll have a value over here that's called the program counter, which is stored by the CPU, and this is going to be start at 0. So what this PC tells us, program counter, is that, hey, CPU, to find the next instruction you want to execute, go to line 0, and then once this instruction runs, actually, since this is going to be 2 bits of data wide, this will be at 2, and this will be at 4. If that makes sense. So this is position 0, this is position 1. So we'll say go to position 0 and execute whatever's there. So it'll find an LDA, and so it'll execute that, and the LDA will come back and tell the CPU, look, I have moved execution forward by 2 bytes. So the PC counter gets updated and then gets set to 2. And so this is the way that we're going to keep track of what's going on, and so the next time it gets to an instruction, it'll come down and execute here. So the instructions should tell us how far to move the PC counter. And then that way we can know how much data was taken, you know, how much data this instruction needed and where it needs to continue execution and yada yada. All right, cool. Another thing here, I'm probably going to be using a lot of classes. It's probably, you know, that you could definitely do it in a more functional way, but I actually really like classes, especially in Python. With stuff like mixins, it seems like it's going to be quite well suited to what we're doing here. All right. Cool. So let's get rid of this. Create the CPU. This stuff can all go up here, actually. So we get the instructions. Now, we're going to tell the CPU to process instructions. I'm going to tell it to load. So the CPU is going to have to maintain some memory. If every instruction is a variable length, how does the PC know how to index the PRG properly? Great question. So the instructions are of variable length, but they are of defined length. So an LDA instruction is of a different length to a, you know, PRQ instruction or whatever. But intrinsically, so if I look at if I look at this, you can see that a BRK instruction is only going to be 1 byte long, whereas a LDA instruction is going to be 2 bytes long. So this LDA is actually separate to this LDA, which is 3 bytes long. So basically, just by reading the instruction bit, which says A9, we're going to know not only what type of instruction it is, but how many bytes the program counter needs to be moved forward to get to the next instruction. So they are a variable length, but we know what those variable lengths are depending on the instructions. So it's just something that we're going to need to implement and then keep track of through the PC counter, which is a register, I think, in terms of implementation. Let me know if that needs more explanation. It should become more clear in time as well. So I think we're going to load all these instructions. So basically, I think what happens is that they will actually get copied from the ROM into the memory of the computer. But I'm not 100% sure about that. It may well just read off the ROM. So, I don't know. Let's just pass in instructions. So let's say process instructions, and we'll pass in some instructions. Now what's an instruction? It's going to be a list of integers. List of integers. Cool. We can get rid of all this stuff now. Cool. So let's go to our CPU and let's go to def process instruction. Interesting. It might even be a better way of doing this would be to create a ROM class, and the ROM class has a set of accesses where you can access awesome, sweet. Where you can access a set amount of bytes. So the CPU is actually going to communicate. So instead of just passing a list of instructions, let's create a ROM class. And the ROM will be responsible for doing all this crap. Bang that over here. And then we can get more of this stuff out of our main code. Basically, I just want the main to be set up, parsing the args, loading, and then all this ROM stuff can actually be pushed to here. So we can get it away and we can abstract everything away, which is nice. So what's a ROM got? So I'm gonna say that it has a data. It has data, which is actually just a list of bytes. And by list of bytes, we're going to pass that in as a list of ints, because that's how we're going to store that. Again, so this is this Python typing system, type hinting. So list is going to come from typing, which is a new module in Python 3.5, which just makes it easier to do what we're doing here. Makes it easier to annotate what you're doing. Cool. All right. So a ROM is going to have number of PRG blocks. So this is again going to be set from the config. So we can do that all in here, but for now we'll just set it to 2. And then we'll set this. This can all move. This is going to be really nice when it all works out. And we're pulling this out of data, which is actually, we'll call ROM bytes. Header size, number, self.number, and programming box. Cool. That looks better. And self.instructions. And they're not really instructions, it's really a collection of bytes. So I'm going to say self.bytes. So bytes is a reserved word, but self.bytes is not. That being said, it's probably bad practice, so I'm going to not call it that. I'm just going to call it self.data for now. Or data bytes or something, who knows. Alright, so let's just give that a bit of a format. Reformat code. Just make sure that's pep80. Cool, so we no longer do that. We no longer need these. We set up our command line arguments. We load the ROM. This all gets done by loading. So ROM equals ROM. ROM bytes. Another thing that Python 3 is going to do for us is that it gives us some keyword only arguments, which are pretty cool. So I might start using them as well. So previously, if you had function parameter A, parameter B, and then reverse equals false. So this would be a flag where you could pass in should, the data that comes out of this be reversed. And so obviously the danger is if you call this function A, B, and then you accidentally pass in like a third parameter or something, this 3 can be set reversed, and then if you're calling if reverse, do something, then this 3 will be taken as true, and that's going to be bad. So what you can do in Python 3 is you can do this, and it basically means that if you pass in this 3 here, it's not going to assign it to this name parameter. It's going to give you an error, and the only way to access that reverse function is to explicitly say reverse equals true. Anyway, we'll come back to that at a later point when we're writing things that need it. List of cool. So a CPU is now going to have reference. So I'm not going to make the CPU have reference to a ROM. I'm not going to pass it in the constructor. I'm going to make it load a ROM because potentially we might need it to copy it into memory later. I'm not actually sure how it works. So we want to be able to change the implementation of how this works. And we'll pass in a ROM. So def load. God. Memory-wise, do you really want to instantiate a new object for every instruction? A giant switch case might be a lot more performant. So, good question. Yes, the answer is almost certainly this is going to be terrible performance-wise. My thought is I'm kind of starting this off with I want to make this as nice as possible in terms of the code, what the code looks like, and not worry about performance at all. I'm kind of hoping that because it's a NES, probably it's not going to be too intense, and we probably should be able to run it even if we're doing stupid stuff like this. If it turns out that it is super slow, then I'll probably change it. But I'm definitely going to prioritize, for now at least, things that look nicer and make more sense to me rather than things that are going to be performant. But I completely agree, because a switch else will definitely be way better, and having things be functions instead of classes and all this kind of stuff is definitely going to be a lot quicker. But yeah, for now at least, I would really the reason that I want to do classes for instructions is because I want to be able to do mix-ins for the different addressing modes. Now, again, I'm not super certain on how all these things work. Like I said, I've just started looking into it, but it would be pretty cool if we could get a lot of this functionality for free and have this line. My thought is, if this works properly, it might be 50 lines of code as opposed to, a couple of hundred. Anyway, we will see. I think the answer to that question is I will definitely fix it later if it needs to be fixed. But yeah, screw that. Let's go with cool code over fast code. That's the way. All right. Instructions. What am I doing? Loading a ROM. So loading a ROM is going to take in a ROM, which is going to be of type ROM. Just so we get our function annotations going. For now, we're going, instead of loading it into memory, we'll just store a reference to it. This is a bad way of doing it, because then we'll have to check if the ROM is none and stuff like that. But yeah, I'm kind of assuming that there's going to be a lot of changes here later, so I'm not going to worry too much about it. Process instruction. Cool. So now, load ROM. So I'm actually going to rename this. This might make more sense, to run ROM. What this will do is load it into memory and then start running it. And then this way we know that a ROM has been set. So instead of process instructions, now we can call, well, let's create a program counter. We know that execution starts at 16 bytes into the code. So we'll set our program counter. This will also, when you're doing jumps and stuff like that, this PC is going to be what we're going to need to change. Alright, self.rom is none. Yada yada. Cool. So let's run an instruction. So the ROM at the moment just stores the data, but really what I want it to be able to do is return. So potentially this might get loaded into memory later, but at the moment I'm going to be querying the ROM and trying to figure out what the ROM wants to do. Okay, so self.pull data or something. I don't know. Get bytes. And position, which is going to be an int. So we're going to get the data, the bit. And it's going to return an int, even though we're talking about bytes. Potentially later I might make it actually everything work in bytes, but I think at the moment I'm just going to make it all work in ints. Oh, God, I don't need to do that anymore. Sweet. Alright. That's pretty cool. It gets the byte at a given position. Cool. So return self.databytes position. Alright, run ROM. So we now want to run through So let's say here we're going to load the ROM. Potentially we might need to copy it to memory or something. Run the program. Alright, so running the program is going to start iterating through this code by starting with this program counter. So while true, this will probably need to be like while the flag is not set or something. I'll say it's running for now. It's probably going to be a flag, so let's just say that running is true. While we're running, we want to read the instruction that is at the program counter. So instruction. Self.rom.getByte at 16. No, at our program counter. So and then we want to turn the byte into an instruction. So we now have a single byte. What do we know about this byte? We know it's going to identify what the instruction is going to be. So we need some way of turning that instruction into the correct class. So what Cadex was saying was potentially just having a giant switch case, which is probably the best way to do it. What I kind of want to do is do something a bit dodgy. Not dodgy, but something a bit more fun. So we're going to create something that is going to map instructions into, bytes, so identifier bytes, into instructions. So for instance, we know, and I'm going to create it here for now, but probably it's going to go somewhere else. So self.instruction mapping. I'm going to make this a dictionary. What we know is there's a set of instructions. So where was load A? Here we go. So A9 is going to be a load A, and we're going to load in a number. So A9 in hexadecimal is, there it is there. So sorry, let me just pull up toggle hex, show hex inspector. A9 is 169. So if we see the value 169, we actually want to load an LDA instruction. Now, because everything is first-class objects in Python, so functions and classes and stuff like that, we can just pass around a reference like this, and then later on we can just create a new one by calling new. I mean, you don't actually call new, but putting brackets next to it will make a new object. So we're just passing around a reference to the class at the moment, not an actual object. So this is not instantiated. Alright, cool. So now we want to turn the byte into an instruction. So instruction equals self.instruction mapping identifier byte. Now identifier byte is going to be an int, and this thing is indexed by ints, so this should work out. Now the thing to do here is going to be to use get and to have it return none. So the if we just use a square bracket syntax here, then if we get an identifier byte that we don't recognize, then the program's going to crash. What we want is to get it and to set a default. So if it can't find it, instead it's going to return none. So let's say if instruction is not none. Let's explicitly check for it. So Python is a bit weird sometimes in that if instruction will work for things like true or false and whether it's none or not, it can be a bit weird. It can have some unintended effects. So for instance, if you think you're comparing you think you're comparing an integer, you think you're comparing a boolean, you're actually comparing an integer or something. So a lot of the time you want to be doing, if you're explicitly checking for nones, like we are here, we can do if instruction is not none, then we want to do something. So here we're actually going to say if instruction is none, we kind of want to throw an error. How do you throw errors in Python? Raise. So we want to raise an exception. And we want to say that exception is instruction not found. Self.pc should be set to header size. That is a fantastic point. Header size is stored in ROM. Yeah, there we go. Self.rom, self.pc equals. I'm actually going to make this, because we might have ROMs that have different header sizes. I'm actually going to unconstant that. And then that way, we can say the PC is actually set to the header size of the specific ROM that we're starting in. This is kind of another Python quirk. Obviously, if you want variables to be recognized by the class, you have to declare them in the init function. Typically, I set these to none, so instead of setting them to 0, because I want to know if I'm here, or if I'm somewhere else, has this ever been set, or is that a default value? So if you set it to none, that's kind of clear to say that, hey, it's never been set. Yeah, this code is already starting to be cleaner, except this needs to be. I might put this on a new line just to make it a bit. God, that doesn't look nice. Reformat code. Yeah, there we go. Nice. All right. Thank you, Kadex. That's a good point. Cool. All right. So if we don't find the instruction, then we want to raise an exception. Potentially we can refactor this out into its own method, just for the sake of less indented code. But for now. So, alright, we're going to start at instruction 16. And now instruction 16 should be this one, which is going to be 78, hex 78, which is where, a stex or something. We looked it up before. Now, we haven't implemented that, so presumably this should raise an exception saying instruction not found. Awesome. Now, here's the fun part. Let's make it work. And to do that, let's implement a 7.8 instruction. Is an SEI instruction. So again, I'll separate these out later, but let's just get 3 instructions going. Obviously, these classes will actually do different things later on. And the last one's going to be D8. D8 CLD. Now, I don't actually know what these instructions do, so I'm not going to properly implement them. But my hope is that it will, we'll implement them properly in due course. And obviously I have some documentation about what these actually do. Cool. Alright. So we need to put them into our instruction mapping. So let's check that here. So 7.8 is 120. And 120 was SEI. And D8 is going to be 216, which is going to map to our CLD instruction. Now again, there might be better ways of doing this. Oh, might be. There are better ways of doing this, but for now, I'm just going to have this dictionary, and then just reference it whenever it yeah, update it for now. I'll come up with a smarter way of doing this later. Cool. So now we should actually get 3 instructions in before we hit an instruction that we haven't encountered before, or 4 instructions in. Instruction not found. All right, that's interesting. So let's see if we're making it. Yeah. So instruction is none. Identifier byte is 2. Get this, get 16. Right, so the answer is I've already offset by 16 here. So the program counter should actually just be set to 0. Now the interesting thing is, I don't think it should be. I think we should be dealing with everything in absolute terms, in memory terms, probably. It's going to make our lives a lot easier. So we do want our PC to start at 16. What we don't want, when we pass in this, we actually want it to get the data. Yeah, so actually, this is our PRG bytes, but the ROM bytes actually start at 0. So, oh god, that's annoying. Alright. So what's another way of saying this? So we don't actually want to index things. When we get a byte, we actually want to give it this position should be relative to ROM bytes, not to the PRG bytes. We don't probably really care about what those PRG bytes are. We just care about the whole thing. Does Python 3 have hex literals? Yeah, that's a great point. I have no idea. Let's look it up. At the moment, I am doing everything in ints. It might be cleaner for debugging to use instead of looking at it. Yes, that is 100% true. My suspicion is that there's the byte representation is probably going to be the closest that you come, but I don't actually know. Yeah, use byte literal. And you can say bytes dot from hex. That's going to be really useful. So probably the answer is what to do is don't store everything as int, store it as bytes. And when I want to refer to a hex thing, I can just type bytes dot from hex. Yeah, you're right, that's going to be way cleaner. Yeah. I just want to check that there's no other things here. Yeah, okay. Yeah, alright, let's do that now. So, we're reading it. Instead of passing it in as a list, so this list is going to turn it into ints. We're just going to pass in the ROM bytes. The ROM bytes, instead of getting a list of ints, now gets in a collection of bytes. ROM bytes. All this logic should still work, I believe. We don't need list anymore. And we want to return this, except this is now going to return a bytes. Interesting. Is a single byte a bytes? I don't know. Let's find out. Presumably this is going to complain if I do this wrong. So instead of this, I should do bytes dot from hex. Sick. Oops. So let's look up the SEI instructions. Here we are. So SEI was, I can just look at my ROM here. So 7.8 is the hex for the first one. And then the next one is D8. Let me just check that D8 is CLD. Yep. Right, so do I just do that? I probably should have done that, check that before. Nope. From hex. Yeah, okay, so I just passed it as string. And LDA was A9, I believe. Nice. Cool, cool. Yeah, let's see if that works. Identify byte is an int, which is probably not what we want. So let's go here. Let's see what these bytes actually are. Self.rom bytes is a collection of bytes. So I think you can't reference an individual byte, is that right? Self.rom bytes 0 equals int 78. So what does bytes.from hex return? Yeah, it returns a segment of bytes. Cool. So what did self.rom bytes? How do I get a segment of bytes? 0 to 2. What if I did 0, 1? Yeah. Alright, so instead of doing this, I can do, instead of directly indexing it, which returns an int, I can just do position and then position plus 1. And that will return me a single byte. It will return me a single byte, but in the form of 8 bytes, which should work. So now when I come down here, my identifier byte is a single byte. Yeah, which is maps to x, which, yeah, is from hex, means 7, 8. Is there a 2 hex? So now if I do identify byte, can I print that as 2 hex or hex? Yeah, nice. Alright, so now we can get the hex representation of a byte instead of passing around decimals. That is going to be way cleaner. Cool, and now our instruction, we can see, is indeed a SEI instruction, which is 7, 8 is what we want. So we now have our first instruction being read in. It doesn't do anything yet, but that's fine. When we get down to LDA instruction, so let's keep going here. So we have a valid instruction, presumably, because we haven't raised that exception out. Valid might be an interesting word. Non-exception raising instruction. Let's see. What do we want to do now? We want to execute it. I don't know what I called the instruction function. Process. I'm going to rename that to execute because I prefer that. Nice. So now, presumably, if we run this code, it's going to print out the first 3 instructions. Ooh, execute missing a positional argument. Fair enough. Doing something dodgy there. instruction. Ah, interesting. I must be using abstract base classes wrong. Derived abstract is derived d.foo, hooray. Huh. SEI instruction is a class. Let's do SEI instruction dot execute. Not passing in self. Ah. Ah, jeez. Okay. I'm not very smart. So instruction is actually, this is going to give us our class. That's what I've done wrong. So if instruction class is known, then, so we want to actually make an instruction. Equals instruction class. Instruction class is not callable. Sure, so how do we... Python instantiate class when that class is an object. Yeah, here we go. Class user equals C1. Oh, so maybe I can't do this. Maybe I can do this. Nope. Ah, because I'm not passing in an identifier byte. Which the identifier instruction now no longer needs. Ah, so I could construct this automatically by making a property of here. But we'll do that some other time. Okay. Look, I'll pass it in. Nice. Now we now have an instruction that is being executed over and over and again. The PC is not getting incremented because we don't ever increment it, so it never moves instructions. So let's create a thing called instruction length. Now actually I can make this an abstract property. And I'll say it returns 1. But instruction length, whereas these ones have an instruction length of 1. So I'm probably going to make this explicit rather than implicit. Can you make this, please? I could. Alright, so we now have a instruction length. So after we've executed that instruction, let's say self.pc plus equals the instruction's instruction length. So now, sweet. So we now are reading in the first three things. Let's give these all a name as well. Whoa. In fact, instead of giving them a name, we can just override their string methods, because that's probably a Python-y thing to do, right? Load A. And instead of execute printing, let's just make it print self.string. And then let's make this. So what we're doing here is we're making the execute method just print the string of the class. We're overriding the string method in each class. And then we will just make it return LDA and the identifier byte. So we are making the string of each instruction tell us a bit about itself. This is a bit more verbose, but it's going to tell us good information in the long run. Sweet. So it tells us the first instruction is an SEI, and the identifier byte was that. Now this isn't particularly useful to us because we can't read this. So let's turn this into 2 hex. Now obviously we're going to be able to standardize this later. In fact, we can do it now because we're going to make this code sexy. Cool. So identifier byte was 78, which makes it an SEI. CLD, which was a D8, and then LDA, which was an A9. Cool. So let's make this nice and generic and say we're going to put the instruction name here and then the instruction byte. And we'll say it's our self.name. So what we're doing here is we're overriding string in the base class. We're going to change this. This is going to be our name. And our identifier byte is going to be this variable. And so we just have to make another abstract property called our name. Undefined. And now we can just say our name is LDA. Now it's a little bit cleaner and looks a little bit nicer, I think. So this single so typically in Python, well in other languages as well, I tend to use a single quotation mark around strings. With the exception of when I'm doing string formatting, I use double quotation marks. That's the way it's done in Ruby. It's just a bit of a convention that I just follow across that. Cool. All right. Instruction class is not callable because it's an ABC, and so it's inheriting. This is something we can figure out later. It works. All right. Cool. So we have 3 instructions now. We read in the file. We know it's SEI, CLD, LDA, and we know what identifier bytes they are. And each of these can have a different execution path. You really gotta hate putting... Yeah, I've been doing some Java recently and it has tripped me up multiple times. Because single quotation marks in Java look and pretend to be strings, but they're definitely not. So yeah, I've been hit by that one before. I don't actually know what they are. They're like byte literals or something in Java. If you put a single quotation mark. It's a bit weird. Oh well. In your Rubies and your Pythons as well, there's no real difference. Actually, in Ruby, you need to have double quotation marks to format strings. But all right. Cool. So now we're executing through the program. They're chars. That makes sense. Does Python have chars? Isn't that was yeah? I'm a bit confused by that, but I think that Python 2 strings were a collection of chars, but in Python 3 they're actually strings. Maybe? I don't know. It's something I should probably look into. Oh well. Alright, cool. So what's next? Making these instructions actually do something, and yeah, implementing more instructions. There's definitely going to be a smarter way to doing this. Instead of having, I might just do that now, instead of having this instruction mapping be constructed like this, probably the easiest way is going to do it is, and this way we don't have to pass in the identifier byte. We can again do, let's put an abstract property on here, which is our identifier byte. Return, great question, none. And this is going to return some bytes. No, yes, yes. This is going to return, I need to get into the habit of doing these function annotations. I presume if I do the base, the rest will be annotated. Things that inherit from it, I suppose. Chars. Cool. And self.identifier byte. Now, we don't need to pass it in here, so our init can just be a pass statement for now. Does a class in Python have reflection over its own name? If so, you could use that and cut off the instruction to save yourself from repeating. Yeah. I don't know. Good question. I'm going to do this and then I'll come back and answer that. The reason I do it is coming from, I've just come off the back of doing some Java programming, so I'm in the, you know, verbose world, but you're right, it's probably a bit overkill to that is to have the LDA instruction be called LDA instruction. Just call it LDA. Alright, so we're going to copy this and then we're going to do some really fun stuff. So this is actually not right. It'll do. So LDA is A9, SEI 7.8, and CLD is going to be a D8. Cool. So now, instead of doing this instruction mapping, instructions, so we can define what instructions does this CPU support. Again, we might put this somewhere different, but and then we can do self.instruction. Mapping is a default dict. And then for, so this is going to be a bit of a dodgy way of doing it, but we're just going to append instructions dot. So we're going to define what our instructions are, and then we're going to... No, I was talking about the name property. Interesting. If I look at SEI instruction, does the class have reflection over its own name? Yeah, I don't know. That is a great point. It does have reflection over its own name. Alright, that's gonna save us some time. Perfect. So the name function will return the name of the class, which means that we don't need to manually specify what the instruction is called. Yeah, which is just going to save us code and time, which is the dream. I'm hoping that eventually as well that these instruction lengths will be set by the mix-ins. So presumably you will inherit from like a single byte instruction or whatever, which is going to be a mix-in. You know, something like that, and then that will set the instruction length and determine how to pull data out and stuff like that for you. Yeah, thanks, Gadex. That's true. All right. Yeah, so now we want to set an instruction mapping and put an entry for the identifier byte. So sorry, to come back to this, so what I'm doing is I'm going to define which instructions are available, and then I'll just put them into a dictionary so I can map out of them later, just by making it a default dictionary so we can put in random entries, map it by its identifier byte, and set it to be that instruction. These are actually not instructions, these are instruction classes. Instruction class mapping, so for instruction class, self.instruction classes. Instruction class mapping should be the instruction class dot identifier byte should equal the instruction class. Cool. All right. Let's think about that a bit more. So this should be instruction class mapping. We'll get you this instruction class. And now we don't need to pass in that byte thing, because it knows what its byte is. To be honest, these might not need to store state, so potentially I could just initialize them. Can't initialize. Right, because I need to remove that name thing there. Cool. All right. Format self.name. SEI instruction has no thing name. Ah. Damn. Yeah, okay. Oh no. No, it's just not a function. Oh, no, didn't work. So that's a property of the class. Can we access our class? Wonder if that's the way to do it. That seems ugly, but... Alright, so we access our class to get our name. Alright, so if I restart this, we have an SEI, a CLD, an LDA, and then we actually have 3 more SEIs. Cool. Sweet. Alright, I think that's a pretty good place. I might stop there and come back. So we've got the ROM is being read in, instructions are being bytes are being read in, mapped to instructions. and then the instructions can define how much to implement the program counter, and we're actually starting to iterate through the ROM. So the next step will be to implement a lot more of these instructions and to start doing them a bit smarter. So to start using some mix-ins and do and do kind of how we read things through that and how instruction length gets determined through that instead of specifying it. Yeah, sweet. I think this is pretty cool. All right, so I'm going to let's see. Why aren't we passing the bytes anymore? Yeah, we are doing that, although I might not have annotated that correctly in all the places. This does return bytes, and I think the ROM returns bytes now as well. Yeah, but we do pass in position. The program the program counter is an int, but we do receive bytes everywhere else. Yeah, all right. I might push this up to GitHub. I think this is going to be a git at all kind of job. And I'll just push this up to GitHub. Sweet. So if I come back to GitHub now, yeah, rock on. So we now have a commit. I did do a PyCharm project files ignore commit, but this is the first real commit. Writing in the NES ROM, sending first instructions to the CPU. I might do a I'll do a tag as well, just to git tag. Do you need quotation marks? I don't know, probably not. So yeah, episode 1. Episode 1. Push the tags. All right, and we should have a tag, 1 release. Nice. Yeah, so all this code is on the GitHub page, which is linked down the bottom of the Twitch. So if you want to go take a look and have any ideas or whatever, I might edit this this README. I probably don't have time to do it now, but I might do it later, and just do some information about, you know, some of the links that I've been going through and stuff like that. Some ideas about what this is going to be. Yeah, if you have any thoughts or questions or comments or whatever, feel free to shoot them over to me. You can message me on Twitch or through GitHub or, you know, or whatever. Yeah, thanks for coming and watching. Thank you very much to particularly Cadex for keeping my code, well, it might not be clean, but or at least putting in a good effort. For Como Andis for having some good thoughts early on. Yeah, I'm gonna Gonna head off. Smiley face indeed. Thanks, Cadex. Yeah, this is the first time I've done something like this, so it's been pretty fun. All the videos will go up on... There is a YouTube that's going to be linked to this Twitch account. So I'll push the videos up, so I'll be recording of everything. I will try to do the next stream tomorrow at around the same time. So I started this one around 2:30 GMT. It might be, yeah, I'll try and do it. Maybe might be around 1:30 GMT tomorrow, so around an hour earlier. Which let me just figure out if I can get a countdown timer to that or something. I'll try and commit to doing it then. Time is, which is a really cool site, but I don't know if I can. Time countdown. Not very. It's almost. That seems good to me. Stream time. Tomorrow. It's 7:17 AM. Jeez. Yeah. Look, I'm not really set to a streaming time or anything. I kind of the idea hopefully will be, as long as I'm recording videos, at least people can keep up if they want. Hi, Little Brown. Thank you for coming and taking a look. Yeah, I'm not really. I'm in Australia, so it's like the middle of the day right here now. It's like 3:18. So I'm pretty flexible with whenever I stream. It could be also at night, which had been around 4 hours, but probably somewhere in this 8 hours or something. We'll have to check out YouTube. Awesome. Yeah, it's a good question. Yeah. I do kind of want to keep a well, not regular, but at least have some kind of countdown to when something's going to go on. But I'm not 100% sure how I'm going to do that. Yeah, if you have any thoughts or any ideas on when I should be streaming, I kind of picked this time at a bit random, but look, yeah, I'll probably say for now that I'll stream at a similar time tomorrow. I started around 3 hours ago, so I'll probably do that, and then yeah, upload things on YouTube at the very least, and yeah, try and do it that way. All right, cool. Thank you very much for watching, everyone. Yeah, I will see you all hopefully sometime soon. Like I said, I think I'll stream at roughly this time tomorrow. Maybe a bit of a shorter one. I'll post on Twitch or something as whether I'm going to do that. James Franco. I wish. Do you only use Python in your streams, or are we going to get some other programs as well? Just a bit curious, as I'm new to this channel. I am also new to this channel. This is my first stream. At the moment, I do obviously program in other languages. At the moment, I think it will be focusing on this one project, which will be making this NES emulator in Python 3. I'm definitely open to doing other programming stuff. I've been doing a bit of Django, which is also Python recently, but bit of Java, doing Android stuff, and I've just come off doing some C++. So look, if you have any ideas or any cool projects, I'd love to kind of like stick around and stream some stuff. Like, comment, and subscribe, precisely. I'll sell out sometimes then. But yeah. Look, as I said, feel free to shoot me any ideas for cool projects or whatever you have. I'm kind of gonna try and push through this one and see where it goes, which is gonna all be in Python. But yeah, I have to say, I kind of have the most experience in Python, so it's all yeah, it's probably the language I'm most familiar with. But like I said, got any cool ideas? This NES project will probably run for God knows how long, but I'm guessing since I've never done an emulator before, made some good progress today, but I'm willing to bet that there's going to be some some issues that we run into in the future, and I don't think that I'm going to try to do all the coding for it on stream, just because it seems like a fun thing to do, get to hang out with some people, so yeah, so it might take a while, so it might be a while before anything else happens, to be honest, a little round. Alright. Cool. Cool indeed. I will see people tomorrow. Yeah, thanks for watching the stream.